Today we are discussing the delta y transformation. And let's see why we are discussing this. Let's take a look at the following circuit. Okay. And let's suppose this is R1, R2, R3, R4, and R5, and these are terminals M and N. What is the resistance, let's call it RMN, seen looking in at terminals M and N? Well, what we've learned so far is to go through and find resistors that are in series or parallel and reduce those and keep doing that until we have one equivalent resistor. So in this circuit, are there any resistors that are in series or parallel? And the answer is no, right? There are lots of resistors connected end to end, but they're not the only thing connected there. There are other things connected. And there are no resistors in parallel connected at both ends. There are, in this case, there are no series or parallel resistors. So we can't reduce this using series and parallel combinations. How can we reduce this circuit? Using the delta Y transformation. Now, a little bit about this. It'll turn out that series, parallel, and delta Y, that's the Greek letter delta, Y, transformations can reduce any planar circuit to a single resistor. Okay, so what is a planar circuit? Well, a planar circuit is a circuit that can be drawn in a plane without any wires or components crossing over each other. So let's take a look at this. Let's say we have, this is kind of now an abstract circuit, so it's just what we call a graph. So we've got these four nodes, we could call them, 1, 2, 3, and 4, and these are branches, which could represent different components, resistors, say. That's a planar circuit because none of the branches cross over each other. If I also connected vertex 1 to vertex 3 or node 1 to node 3, that's still a planar circuit. What if I connect 2 to 4? Well, that would seem to not be a planar circuit because you've got two branches crossing. However, I can redraw the circuit so that they do not cross. Okay, so I can keep this like so. And this connection, here's 1, 2, 3, 3 and 4. The connection from 2 to 4 I can draw like this. I can redraw it so it does not cross over. So that is a planar circuit. Now, on the other hand, I look at this this circuit here. One, two, 3, 4, 5 vertices, and they're all mutually connected. Like so. Kind of a star shape there. Try as you may, you cannot find any way to redraw that circuit so that it is planar, so that none of these branches cross over each other. And there's a result from graph theory. And it says the following. A planar circuit with n greater than or equal to 3 nodes or vertices can have at most 3n minus 6 branches. Okay, let's see. So up here we've got 4 nodes. So 3 times 4 is 12, minus 6 is 6. So we got 1, 2, 3, 4, 5, 6 branches. So we expect that this would be a planar circuit. We should be able to redraw it, as we were able to, so that no branches cross over each other. Now over here we've got 5 nodes. 3 times 5 is 15. Minus 6 is equal to 9. So we can have at most 9 branches. And what do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 branches. So this has more than 3n minus 6. So this cannot possibly be a planar circuit. Okay. So this is a planar circuit. None of these resistors cross over each other. None of the branches cross over each other. So we should be able to reduce this using series, parallel, and delta Y. We've just seen that we can't use series or parallel because there are no series or parallel combinations. So we need this idea of the delta Y transformation. Okay? So that is our motivation for delta Y transformations. Now, in general, if we have a non-planar circuit, even a delta Y transformation won't allow us to reduce it to a single resistor, and we'll see some techniques later that we can use, called the node voltage method, that we can use to do that reduction. But for our purposes, all the circuits we'll look at will be planar, and so these 3 transformations will be all we would need. All right, so let's now introduce delta and Y configurations, and then the transformation. So suppose we have 3 nodes here. And we're going to draw the connections like this in a triangle. And this is node A, B, and C. We'll call this resistor RA. This is resistor RB. And this is resistor RC. This is going to be called a delta configuration. This looks like an upside down Greek letter delta. And then those same 3 nodes A, B, and C here, we can also connect it with resistors as shown here. And we'll call this R1, R2, and R3. This is a Y configuration. It looks like the letter Y. And the delta Y transformation allows us to transform from one of these configurations to the other. Now, we could redraw these. Let's redraw the one on the left. And it's pretty often the case on our schematics, we only want to have components that are either vertical or horizontal, not at an angle. So we could redraw the first configuration like so, without changing the way it's connected. Right? So this is C, this is A, and this is B, and this is RC, Ra and Rb. And this would be called a pi, like Greek letter capital pi configuration. And it is the same as the delta. It's just drawn a little different, but the connectivity between the different nodes and through the resistors is exactly the same. Okay, so these are the same. These are equivalent. And for the Y configuration, we could flatten this out to make what's called a T configuration. It would look something like this. Here's A, B, and C, R1, R2, and R3. So this would be a T configuration, which is equal to a Y configuration. So like in power systems, it's very common to see these delta and Y configurations and hear those terms, delta and Y. In electronics, we may more often see them drawn as this pi or T type of configuration. So it's the same thing. So when we say delta Y, it could be a pi T type of transformation. All right. So how do we go about doing this transformation? Well, we want these two circuits to be equivalent with respect to the three terminals A, B, and C. So what does that involve? So let's redraw this. These circuits on top of each other in different colors here. A, B, and C. This is RC, RA, RB, R1, R2, and R3. Okay, so these two networks will be equivalent to each other if the resistance between any two pairs of the nodes is equal. That is, if the resistance between nodes A and B is the same in the two networks. Well, let's see. What is the resistance between A and B in the Y configuration? That's the red resistors. Well, let's see. We'd have a path here through R1 and R2. So it would be R1 plus R2. All right, there's no path from C to B, so or A to C directly, like that. Okay, so the current would just flow like so. Great. How about in the delta configuration? Well, now we would have a path here from A to B, which would be RC, but that would be in parallel with another path that goes from A to C to B. So that would be RA plus RB. So they would be in parallel. And looking at the other pairs of vertices for B and C, is kind of the same thing, just rotated there 120 degrees. We'd have R2 plus R3, right? So R2 plus R3, and then RA parallel RB plus RC would be for the other network. So that would be RA parallel RB plus RC, and then for RC to A, well, you can see that what happens here, we're just cycling through the subscripts. This would then be R3 plus R1, and that would be equal to RB parallel, let's see, ABC, RC, BCA, and there you go. So if we can satisfy these conditions, then these two networks of each of three resistors will be equivalent, and we can exchange one for the other in any circuit. And this is the delta Y transformation. Now, these are three equations. And let's say we know Ra, Rb, and Rc. Well, then there are three unknowns, R1, R2, and R3. So it seems like we should have three equations and three unknowns. And indeed, we do. Okay. So let's see. How can we do that? Let's say we know Ra, Rb, and Rc. We want to find out R1, R2, and R3. Let's see. So if we add the first and the third equations, we'll have R1 plus R1, 2R1 plus R2 plus R3, and then we could subtract the third equation, which is R2 plus R3. Okay? So this is what we could, so if we call this is equation 1, 2, and 3, we could say then 1 plus 3 minus 2 is going to be 2R1. Again, R1 plus R1, and then R2 plus R3 minus R2 plus R3. Those will cancel out. Okay, so what does that look like? It's this plus that minus that. So let's put that down here. So it's going to be RC parallel RA plus RB plus RB parallel RC plus RA minus RA parallel RB plus RC. All right, let's look at this first expression here. RC parallel RA plus RB. Okay, what is that? Well, it's the product, so that'll be RC times RA plus RB over the sum, which will be RA plus RB plus RC. Now, from what we just did there, we can see that for these three terms, we're always going to get the same denominator, RA plus RB plus RC. And so our 2R, which is equal to this thing here, 2R1, sorry, is going to be over a common denominator. And it's going to be over R1 plus R2 plus R3. And we're going to have RC times RA plus RB plus RB times RC plus RA, and then minus RA times RB plus RC. Okay, here we've got an RA-RC, and here's a minus RA-RC. Okay, so those cancel. Here's an RC-RB, and let's see, here's a RC-RB, but not with a minus. This is a minus RA-RB. Do we have any RA-RB? Here's an RA-RB minus RA-RB, so that will cancel that. Now, what does that leave then? We've got RC-RB, and here's RC-RB. So that'll be equal then to 2 RC-RB, or let's put them in the other order here, RB-RC over RA plus RB plus RC. Okay, and there's a common 2 in both of these expressions. We can cancel that. And so there is our expression for R1. R1 is RB RC over RA plus RB plus RC. Now, if we did the same thing with R2, right, because we're just basically then it's the same as just taking the same whole thing and rotating at 120 degrees and doing the same kind of calculation. We're just going to have different subscripts. So if we go through and do that, what we're going to get is RC RA over RA plus RB plus RC. And finally, R3 is equal to RA RB over R1, RA plus RB plus RC. Okay, so that gets us our R1, 2, and 3 from our RA, B, and C. And it's convenient to write these formulas in a somewhat modified form. Notice up here in the numerator, in each of these cases, we have a product of two of the resistors of RA, B, and C. So if we multiply that by the third resistor, so we have RA, B, and C in the numerator, let's call that RP squared. Call that RA, RB, and RC, the product of the three over the sum, RA plus RB plus RC. And of course, the numerator is going to be ohms cubed, and the denominator is ohms, so this has units of ohms squared. It's a square of some resistance. If we do that, then these three expressions become rather simple, and it is that R1 is RP squared over RA, because this just has B and C. So if we divide by RA, we get rid of that RA factor and we get this expression. For R2, we want to divide by RB because then it leaves you just A and C. Okay, so R2 is RP squared over RB, and R3 is RP squared over RC. So this is convenient. You can just up front calculate this RP squared and then reuse it. So convenient for a calculator. Okay, and we can go the other way. Of course, with these expressions, we can immediately solve for RA. Right, just cross multiply and then divide by RA and then divide by R1, and we get RP squared over R1. And RB is RP squared over R2. And RC is RP squared over R3. Now, to use this, of course, we would need to be able to express RP in terms of R1, 2, and 3. So what is RP? It's the product over the sum. Okay, well, we can then just solve for, what we can do is come in here and take this expression, this is RP squared, and just plug in what our RA, B, and C are in terms of R1, 2, and 3, right? We can say here, RA is RP squared over R1, and then we'll have RP squared over R2, and then for RC, we'll have RP squared over R3, and that will then be over RA, which is RP squared over R1 plus RP squared over R2 plus RP squared over R3. Okay, and then that's equal to RP squared. Okay, so we can cancel, divide by that RP squared. That gets rid of one of these RP squareds. And then divide through by RP squared and top and bottom. Of course, this then leaves just a 1. And divide through by RP squared and top and bottom. That gets rid of another RP squared. And then from that, well, let's just multiply through here by 1 over R1 plus 1 over R2 plus 1 over R3, and then multiply by R1, R2, R3, and then that leaves RP squared is equal to, and here's what the expression is then, RP squared is equal to R1, R2, R3 times 1 over R1 plus 1 over R2 plus 1 over R3. Okay, so these expressions right here, oops, let me do this. can be used either to calculate the R1, 2, and 3 from Ra, B, and C, or go the other way. And we would use one of these two formulas to get the Rp squared, whichever one would be appropriate. So that is the delta Y transformation. And just like parallel transformations, it's important to understand this works regardless of what other things might be connected to the A, B, and C terminals, right? As long as we can isolate one of these two structures, either the delta or the Y, or the pi and the t, then we can do this transformation. So let's see how that works. So let's return to our original circuit that got us started here. We already said there are no series or parallel combinations. Are there any delta or Y or equivalently pi or t configurations here? Well, we can see here R2, 3, and 5, they form a pi, right? It's a pi configuration, right? This kind of a structure. And R1, 3, and 4 is an upside down pi. And then R1, 2, and 3, well, that looks like a T rotated 90 degrees clockwise. So take this and rotate 90 degrees clockwise, and you've got this right there. And then likewise, R4, 3, and 5 would be a T rotated 90 degrees counterclockwise. So we could use any one of those. Let's use R1, 2, and 3. And so that's a T. So we're going to go to a pi. Okay, so let's redraw this now. Let's spread this out to isolate R1, 2, and 3. So let's do the following. Like so. So there's R1, R2, and R3. And let's call this A, B, and C. Okay, now where does that fit into our original circuit? Okay, so that takes care of these resistors right there. So this would be our node C. And so from node C, we have R4. And then R4 also over here is A, and here's B. So R4 goes between A and C, and R5 goes between B and C. Okay. So let's draw that, stretch it out here. So this is R4 goes between A and C, so we can connect it like so. And then R5 we'll put down here, goes between C and B. And then these are nodes M and N. M and N. Okay, so now we're going to transform R1, 2, and 3, this T, into a pi. So let's come over here. And so let me make this centered so it'll go like this. That's still C. Now, R1, 2, and 3 will transform. 1, 2, and 3 will transform to A, B, and C. This will be A, B, and C. Okay? And then again, this is node A, and this is node B and node C. And now we just need to reconnect this. Here's A, B, and C. Just reconnect what the remainder of the circuit, and that's what? Just R4, which goes from A to C. A to C. Well, we could draw that like this. There's R4 from A to C, and R5 goes from C to B. C to B. Well, we could draw that like this. There's R5. And where's our M and N? Well, let's see. M is the same as A, so it would be up here. Let's do it here. And N is connected to B. It's the same as B, so we could put it out here. N. Okay, so we want to look now at our resistance RMN in those two terminals. Now, do we have anything in series or parallel? Yes, we do. These are in parallel, and those are in parallel. So what does this look like? Well, then it reduces down to the following circuit. Here's RC, M and N. And then up top, we've got R4 parallel RB, or RB parallel R4, either way. And on the bottom, we've got R5 parallel RA, or RA parallel R5. And now we've got, these are in series, and then that's in parallel with RC, so we can see now that our MN is going to be equal to RC parallel RA parallel R5 in series with RB parallel R4, and that's our final answer. Okay, and what are RA and RB? Well, here they are, RA and RB and RC. And what's RP? Here it is. All right, so. Okay, so that's an example of the delta Y transformation. It's more complicated than a series and parallel, right? Series is the simplest, you just add. Parallel is a little more complicated. You add conductances, which is equivalent to taking the inverse of the sum of the inverses. And then delta Y transformation is a little more involved. Let's do some more examples. Okay, let's do a pi to t transformation with some actual resistive values so we can calculate instead of just having an algebraic expression. Get some numerical expressions here. So here's A, B, and C. Up here we've got a 1.5 kilo ohm resistor. On the right, a 2 kilo ohm resistor, and on the left, a 1.2 kilo ohm resistor. And let's see, this is node A. The resistor that's opposite it, not connected to it, would be RA. Here's B, the resistor opposite that would be RB. And here's C, the resistor opposite that would be RC. And we want to convert that to a T configuration. There we go. And here's A, B, and C, R1, R2, and R3. Okay, how do we get R1, 2, and 3? Well, here's our formulas. RP squared over RA, and etc. So we need RP squared in terms of the RA, B, and C. Here it is, product over the sum. So RP squared is the product. So that's 2K times 1.2K times 1.5K over the sum. 2K plus 1.2K plus 1 plus 1.5K. And that is 76,000 ohms squared. Then R1 is Rp squared over Ra. What is Ra? It's 2K. Punch those numbers. This divided by that, you get 383 ohms. R2 is Rp squared over Rb, which is 1.2K. And that's 638 ohms. And then R3 is Rp squared over Rc, which is 1.5K. And that is 511 ohms. These are all to the nearest ohm. So 383 638 and 511. And those two circuits then are equivalent with respect to terminals A, B, and C. And you could just check, for example, let's look at Rab in this circuit, right? The resistance between A and B, well, that would be 1.5K in parallel with 1.2 plus 2. So 1.5K in parallel with 2. Well, we can just do that by 2 plus 1.2 is 3.2. So 3.2K. And that is equal to 1.02K. And then over here, it would just be R1 plus R2. And that's 383 plus 638, and that indeed is 1.02 kilo ohms to the little bit of round off error there. Just it would be actually 1.01 kilo ohms, because 3 plus 8 would be 11, but a little bit of round off error because we're going to 3 digits. Okay, so that just is a check, right? You could check from B to C and A to C and so on. Good idea to make those checks just to make sure you did the calculations correctly. Let's look at another example now. We've got this circuit here. And here will be node M and N. This is 300 ohms, 250 ohms, 200 ohms, 100 ohms, 400 ohms, 350 ohms, and 150 ohms. What is the impedance between, the resistance between nodes M and N? RMN equals what? Are there any resistors in series or parallel? Well, yes, we can identify these two resistors as being in series, and these two resistors as being in series. Okay. So with that reduction, then we're going to get the following circuit. 300 ohms, 250 ohms, 200 ohms. Let's see, 100 plus 400 is 500 ohms here. And 350 plus 150 is also 500 ohms there. Okay, and again, here's M and N. Okay, anything in series or parallel? No, there is nothing. You might be tempted to say these two are in series, but remember, we want to find the impedance between these two nodes. So we would actually have to be connecting something at those two nodes with an ohm meter. So we can't take these in series because that would get rid of node M, node M and node N if we connected these two in series. So that's as far as we can go. So we can look at this now, and we could, for example, say these three give you a pi type of structure. These three in the middle are T. Here's a pi. Let's go with the middle T. Let's do a T to pi on those. All right, so let's see. This is going to be, now remember when we have the T configuration, that's when we have the R1, 2, and 3. So we're using these formulas now with using R1, 2, and 3. So we've got R1 is 300 ohms, R2 is 250 ohms, and R3 is 200 ohms there. So Rp squared is R1, R2, R3 times 1 over R1 plus 1 over R2 plus 1 over R3, and actually a little more economical formula as far as we're using on a calculator is to multiply these out. This would just take out the R1 from this product, so you'd have R2, R3. The next one you'd take out the R2, so R1, R3, and the final one you take out the R3, R1, R2. Okay, so let's just plug in R1, 2, and 3 into that, and we get 185,000 ohms squared. And then we're going to replace that with a pi circuit. It looks like this. Here's going to be node C. This is RC. This is node A. This is RA. And this is node B. And this is RB. Where RA equals Rp squared over R1, right, which is over 300. And to 4 digits, that's 616.7 ohms. Rb is Rp squared over R2 over 250. That's 740 ohms. And Rc is Rp squared over R3 over 200, which is 925 ohms. Those are all the 4 digits, 4 significant figures. Okay, so now we're going to plug this in and replace that and see what's going to happen there. Rb is going to go now in parallel with the 500, Ra in parallel with this 500, and then we'll have a single resistor across here. Okay, so this is what we end up with then. We make that replacement, and we've got our pi here. And this has Ra is our 616.7. Rc is 925. And Rb is 740. Okay, and that's replacing this structure. And so then we would have this 500 on the left and the right. We'll just go down on the sides like this. And over here. And we want the resistance between M and N. That's between there and there. Okay, well now we've got parallel and parallel. And then those are going to be in series. So let's first do the parallel combinations. So 500 parallel 740 is 298.4 ohms, and 500 parallel 616.7 is 276.1 ohms. So this is going to be 276.1 ohms. This is 298.4 ohms, and we still got 925 up on top, and we want the resistance between M and N. So now these two are in series, and then that's in parallel with the 925, and so we can write that RMN is 925 in parallel with the sum of these two, 298.4 plus 276.1, and that is to 3 digits, 354 ohms. And so that's our final answer for that. Let's do one more example. Consider this circuit. And I won't put the ohm symbol on here just for economy of writing. These are all in ohms, 24 and 47. And then we want the resistance between the top and bottom here. So we want the R equivalent seen at those two terminals. Well, it's a planar circuit. Are there any series or parallel combinations? No, there are not. So we must be able to do this with a delta Y. So let's identify the bottom here as a delta. So this will be A, B, and C. 33, 47, 24. This is RA, this is RB, and this is RC. Okay, so we need the RP squared, and the formula in terms of the RA, B, and C is the product over the sum. Okay, so that's going to be 47 times 24 times 33 over the sum. 47 plus 24 plus 33, that is 357.9 ohms squared. And then R1 is RP squared over RA. So that's this over RA, which is over 47. That's 7.615 ohms. R2 is RP squared over RB. That's over 24. That's 14.91 ohms. And R3 is RP squared over RC, and that's over 33. That is 10.85 for significant figures. Okay, so now, all right, our Y is going to have this kind of a structure. So we're going to replace this with the delta with the y. And now what are we going to get? It's going to look like this. Now we've got the y here. Okay, so we got 51 and 27 on the top. And then we got the y values here, 1, 2, and 3. So we got here's 7.615 and 14.91 and 10.85. And here's where we're trying to calculate our equivalent resistance. And so now these two are in series and those two are in series. And then those are in parallel. And then they're in series with 10.85. So our equivalent is 10.85 plus this series combination, which is 51 plus 615, sorry. And that's in parallel with this series combination, 27 plus 14.91. And we punch those numbers and we get 35.3 ohms as our final answer.